Good afternoon, everyone. So I'm PEDRO FIGUEIRA. I come to you from the Center of Astrophysics. Oh, sorry, the name change. The Institute of Astrophysics and Space Sciences. And I would like to present you the last work I did in collaboration with several colleagues of mine from the same institute. I work mostly on instrumentation, but I just happen to be a very nosy guy, so this is about something completely different, as Monty Python would say. So basically, the outline of this is in exoplanetary science, we work a lot with correlations. As observers, we try to understand how things correlate with other things. And this idea started with a puzzling correlation, which we tried to understand. And how we acquired new data, how things got more complicated, as they usually do before they become simpler again. And the results and what they mean, and how from something as boring as a statistical study, we could reach a very interesting conclusion. At least that's how I see it. So, from the beginning, puzzling correlation. So yesterday you saw several interesting talks from Vardan, from Phil, and today again from Niku on how the stellar properties gives us some insight on the exoplanetary properties. And for me, one of the most puzzling correlations on top of those that we could understand more or less easily, such as the impact of metallicity on formation and several effects, several things we know about formation, like we discussed right before. So on top of the very easy or easier to understand correlation, there was one that I found extremely puzzling since the beginning when it was introduced, the correlation between planetary surface gravity and activity index of the star. And before I go into numbers and plots, let me explain you where this came from. So you have a star, and we know and a planet orbiting around it, and if the planet transits, you can determine the radius of the planet and the mass of the planet. And as such, to calculate the gravity on the surface of the planet is just a number, just simple application of Newton's gravitational theory. On top of that, we have a lot of spectra on the star, and as such, we can obtain very high composite spectra with very high signal to noise, and to determine with fine detail the several spectral features on the stellar spectrum. One of the most interesting is the activity index, which is used to characterize stars in terms of activity. And it corresponds basically to calculating the flux inside some of the deepest absorptions of the calcium lines, and to calculate the emission inside these lines compensated or corrected for the photospheric emission of the star. So what we want to measure is just the activity coming from the star on the external layers of the atmosphere. So what happened in 2010 is that Hartmann published this interesting correlation between planetary surface gravity and stellar activity. And when he published this, no one had an idea where this could come from. And I looked at it and I said to myself, well, let's wait for a bit and we'll see how this turns out when we have much more data. And a couple of years elapsed. And at some point I said to myself, we can look at the literature, we can collect the data, and in 2014 we had a data set which was basically 3 times larger. And on top of these points here, which were the original points, we had several other points around, scattered on the activity versus planetary gravity plot. I have to say that this beautiful correlation you see here is a correlation which results of the selection of the points. Here you have all the points which correspond to the condition 3, so basically no restriction. Then you have a condition that was applied basically to select stars for which the activity index was calibrated. This seems reasonable, condition 2. And condition 1, which you see in black, and that represents the strongest correlation, was a condition for which only the stars that were well calibrated in activity were selected, and stars hosting hot Jupiters, basically. Massive closer-by planets, to be precise. So you have this beautiful correlation here. So with our new data set, we tried to apply the same conditions. since we have the SweetCat catalog that was presented yesterday, we had a very good measurement, a very homogeneous measurement of effective temperature, and as such could determine in a precise way which stars were inside or outside the calibration. And we applied also the condition on the hot Jupiters, or on the close-by planets, close-by massive planets to be precise. And we have in these plots the original plots with different conditions on temperature from the literature and from our new catalog. And here, the new data set, again with temperatures from the literature and the new catalog selected, and the points in black represent, out of those that have the right temperature or the right temperature domain, the massive planets. So you can tell me that if this is not a correlation, this is even less of a correlation. And you're probably right. But we know that our eye can fool us, and as such, we calculated the correlation coefficient for all the different conditions, for all the different cases, for the different types of temperature, and for temperatures defined by the SweetCat, for temperatures that were defined by the literature. And what we concluded was that the correlation coefficient was still high enough so that it could not be obtained by a chance alignment of the points. Now, we had a lot of points, and it was very hard to align them by chance and to reach this correlation level. And this was a little bit frustrating because when I decided to look at this data, I had set my own mind that the correlation was not there. So I had to come to terms with that personally and evolve as a human being and scientist. And we searched for a lot of alternative explanations. Maybe there was something wrong in the data. Maybe there was a correlation that found its way into the final result that we had. Maybe we had a correlation between mass and activity index. Maybe we had a correlation between radius and activity index, effective temperature and something. And after 10 pages of paper, we concluded that there was nothing that could explain this correlation. It should be there. There was no bias we could identify. The correlation should be there because of physical reasons that we didn't know. And interestingly, when our paper was accepted, another paper was accepted on the same volume and edition of A&A, a letter by Nuccio Lanza that explained that, in fact, this can be, what we see might be an observational consequence of the evaporation of a planet. The planet, the close-by massive planets, might be strongly evaporated by the star in such a way that they will absorb preferentially the activity index and only the activity index. And this is an extremely interesting explanation, not only because it's by far the best explanation that we have, but also because it has strong implications on, one, the usage of the activity index to monitor stars, and two, on what we know about evaporation and mass loss on planets. These are parameters that are very poorly constrained, and every information we can try to get on them is extremely valuable. So, as such, I would point you to this paper, which basically takes a fresh look at this correlation between stellar activity and planetary surface gravity, which points to this new explanation by Nuccio Lanza. And that's it. Thank you for your attention.